So different ways to compound. What we've seen so far is that we can compound annually our investments, and we end up with this formula, that the balance as a function of time is the starting balance, denoted B sub 0 or B naught, 1 plus the rate to the t. Now, for the sake of these problems, we're going to let t equal number of years. Okay. Then we also looked at monthly. And monthly is B of t equals B0 times 1 plus. And what happens in the monthly case is you get a little piece of interest every month. But for every year that goes by, whatever t is, you get that interest 12 times. So that's why we do 12 times t. Okay? And then I think we talked about daily. We talked about weekly also. I'll skip that. But daily, B of t equals B sub 0, 1 plus the rate. You get 1/365th of that rate every day. But for every year that goes by, you get that 365 times. Okay. And then what we finally arrived at is the idea of compounding continuously. So this is sort of like saying, I don't only get interest like every day, I get interest every fraction of a second per day. And, if I was going to get interest 4 million times during the course of the year, right, then I get 1/4 millionth of the interest rate per unit of time, and I get that 4,000 times. What we saw with the chart yesterday was, in this strange investment strategy where we invested $1 at 100% APR for 1 year, what we noticed is that we never really got beyond some magic number, which I called E. I told you this was the number E. Okay? So how does the compounding continuously formula work? It works like this. Your balance is a function of time. Starts off the same way, B sub 0. And it turns out it's going to be E to the rate times time. You might say, well, why is that? Well, I'm skipping a few steps, but if you think about what happened yesterday, B0 was 1, right? R and T were both 1. The interest rate was 100%. So we just ended up multiplying B0 by E, right? But if the rate is less than that, we end up doing E to that power. That's basically what happens. It comes from this idea. What we said yesterday was that as x goes to infinity, in other words, if x gets really, really big, then this expression, 1 times 1 plus 1 over x to the x power, okay, gets really close to E. That's what happens. I should say, we'll just say, well, it can say equals E or approaches E. All right. Now there's something called limits, which you'll learn about later. But this is the first introduction to the idea of a limit, sort of saying, hey, what happens when x gets really, really huge to this expression, and it starts to get close to this number E that we talked about. Okay. So the only thing that's different, sometimes you might ask, well, what about this? Suppose I have this expression, R over x to the x power. Well, it turns out, if you go through all the steps again, what you end up noticing is, like if the rate instead of being 100% was maybe 4%, the number you get really close to turns out to be E to that rate. That's what happens. Okay? And then the last case, suppose you're going to let x get really big again, and instead of starting at 1, you start at some number like B0. What do you think that gets close to? The goal of yesterday's lesson was to get all of you to believe that as the number of compoundings gets really big, that this balance, right, just zooms in on some number that's like 2.7 something, gets closer and closer to something. So I'm not really proving why that happens or anything, but what I am saying is that number it gets close to has a special name. It's called E. And it turns out that for compounding continuously, in other words, if we let the number of compoundings get really, really large, then in effect you get this formula, okay? This formula right here, okay? And what I'm attempting to do here is sort of justify, give you some sense of why that's happening. Well, this last case, if you notice, this expression here is just like this expression, except it's being multiplied by b0. So you would expect this to be b0 e to the r. Okay? All right. So what does this mean? It means that if we were going to compound many times for just 1 year, we would have e to the rate multiplied by the initial balance. And then lastly, if I want to do this t times, in other words, if I want to do this for more than 1 year, then that means I'm going to take this thing and I'm going to multiply by that t times. We're putting it to the t power, which means multiply by that t times. And then to finish off, you end up with b0 e to the r t. And we know that's e to the rt because we know the following. We know that this piece here is e to the r. So here it is. That piece is really e to the r. But I'm putting that to the t power. And you learned a long time ago in Algebra 1 or an earlier course that in this situation you multiply exponents. So you get e to the rt. And so that's where that's coming from. And then we're multiplying it by b0. Okay, so sort of an interesting question is, let's compare these different investment strategies and see, what works out best for us, and, that kind of thing. All right, so what I'm going to do is I'm going to start by making comparison for some investments. So let's pretend we have some theoretical banks to pick from. So Bank A does the following. They do 7% compounded daily. Okay. Bank B, okay, does 7.1% compounded monthly. And then lastly, there's a third bank, Bank C. This is the smart, geeky bank. They do the following. They know how to compound continuously. They know the formula that we just talked about. So they give 7.05% compounded continuously. Okay. So the question is simply, which is the best bank to invest in? So to answer this question, let's just pick an amount of money to invest. When left to my own to pick, I like to invest $100. And the reason I like to do that is for some reason, let's just say, at the end of one of these problems, we end up with $108. Then I can see that my investment increased by 8%. So I kind of like to use $100 as an investment when possible. And I don't know if that's going to happen or not. We'll have to see. All right, and then we need to invest for a certain amount of time. So that's up to you. You could just do 1 year, or you could do many years. We'll do 1 year for now. Okay, so for Bank A, since they compound daily, they're going to take the $100. They're going to multiply it by 1 plus 0.07 over 365 to the 365 times 1. Okay, and if we multiply that out, we'll get some kind of number. I'll make this comment. Put your 365 times 1 in parentheses. It's not going to matter for the case where we're dealing with 1 year, but if you're going to invest for 5 years and you didn't put 365 times 5 in parentheses and you left the 5 down to the right, it would not give you the correct answer. Okay. So this is about 107.25. Sort of a fun thing to think about is that means our investment really increased by 7.25%. Even though the advertised rate of this bank is 7%. They're actually giving you a little extra 0.25% because of the way they're compounding. Okay? If you ever gone to a bank, sometimes they say effective yield. That has something to do with that. All right, let's consider Bank B now. So Bank B is going to compound less frequently, but at a higher rate. So $100 times 1 plus 0.071 over 12 to the 12 times 1. If we type that in, so we get $107.34. So you can see in this case we actually increased by 7.34%. So far Bank B is in the lead. Bank B looks like the best place to go. Let's go to this last bank and see what they tell us. All right. So now we're going to compound continuously. So it's going to be $100 times E. Now it's E to the rate, not 1 plus the rate. So it's just going to be 0.0705 times 1. Okay? So go to find the calculator, the button on your calculator for E. Okay? And we type that in. So it looks like you're getting $107.30. Okay? So in this particular case, it looks like Bank B wins. All right? And you may or may not be surprised, but we sort of saw the other day that as you increase the number of compounding periods, like in this chart, you did not see as big a jumps in the balance when you went from, say, 365 daily to minutes, 525,600. You didn't see a huge difference there. 365 is 2.714. 5,525,600 is 2.718. So you don't see a big difference there, but going from, say, annually to monthly, you see a huge difference of 0.613. And what this problem just does sort of confirm that even though we thought maybe compounding continuously might make up for the fact that the rate was lower, but it really didn't, because going from monthly to compounding continuously doesn't mean a huge difference, all other things being equal.